Before we start looking at carburetors specifically, or the hardware, we need to step back a little bit and understand the principles, the scientific principles that govern how a carburetor works, how we get this fuel mixed with the air as it goes through. So here is the scientific principle, and a lot of it comes down to a guy named Bernoulli. There's a guy that you need to remember his name because he discovered a principle that is really key to these carburetors. But first, let's look at this concept of flow continuity. And I've got equations up here, and we're not going to do a lot of math with this, but I like to put the equations up there so we can start to see that it's a mathematical relationship that's really governed by math of how these carburetors work. So the first principle I want to look at is this principle of flow continuity. And this equation says that the flow rate, Q, through some pipe or something like that, is equal to the area, the cross-sectional area of that pipe, and the velocity times the velocity, how fast that material is moving through there. So let's think about this. If I've got a pipe and I've got a certain amount of material and I'm pushing it through that pipe, there's going to be a certain velocity. That material is going to be moving at a certain speed. So now let's think about what happens if I take that pipe and I squish it down. I make it smaller. So I constrict it. And I'm putting the same amount of material through that pipe. What's going to happen? The only way I can get that same amount of material, the same flow rate of material through that pipe, is it's got to be going a whole lot faster than it was before. So with a bigger pipe, everything's going to go slower. With a smaller pipe, it's going to make things go through faster. So that's one of the principles. Well, now Bernoulli, he studied flow rates a lot, and he looked at that flow rate change and stuff like that. Okay, if the area goes up, the velocity goes down. The area goes down, I get a small pipe, the velocity has to go up. And he said, you know what? There's also a relationship between that velocity and the pressure in that pipe. So what that means is that the pressure in the pipe and the velocity at one place in the pipe, if I change the velocity and the same amount of material going through that, it tells me that the pressure is probably going to be changing as well. Now, we also know that there's a little bit of a density relationship in there, and so we could dig really deep into this mathematically, but I want to just understand the basic principle is what happens. So we're going to go to a situation like this where I have a pipe and I have material flowing through this pipe. And you see that I neck this pipe down. I restrict it. I have it go down to a small diameter. Think about what's going to happen to the material that's rocking along here at a certain velocity, and it hits this restriction in the pipe. If all that material has to get through that restriction, that means that material's got to go really, really fast. And after it gets through there, then it can slow back down again. So all those particles are going to have to speed up as we go through there. Now, we have a name for these. You've probably seen this kind of a thing in a pipe. We call this a venturi, V-E-N-T-U-R-I. And that's when Bernoulli started looking at these venturis and saying, you know what? As that material goes through there, if I have a certain pressure up here, as it speeds up and goes through here, I'm going to have a different pressure. In fact, it's going to be a lower pressure. So what Bernoulli said is, hey, if I've got certain conditions over here on the left side of this equation, and I go to the right side of the equation and my velocity goes up, the only way to keep that equation equivalent is that my pressure here has got to go down. So I have the same kind of relationship I have with the area and velocity and the pressure and velocity. It's the same principle that makes an airplane work. So you've probably seen an airplane wing. If I hold this paper up like this, you kind of see the shape of the airplane wing. And we know what happens when you blow on the bottom of that piece of paper. The paper is going to go out. But what's interesting is that when we blow on the top of the paper, we're also going to get that wing to come up. So you see how that paper lifts up? And I'm blowing out across the top of that paper. What's making that happen? The air, as it goes across the curve of this paper, has got to go a lot faster than the air underneath the paper that's going underneath it. So as that air goes up, the pressure, the speed goes up, the velocity goes higher, the pressure goes down. So I get a negative pressure, and it wants to lift up on that paper. So it lifts the paper. That's what makes an airplane wing fly. It's the same principle that's going to make a carburetor work. So when I go down into this small constriction, the velocity is going to have to go up, and that means the pressure is going to go down. How does that work in a carburetor? So let's take a look at the cross-section of a very simplified carburetor. So this is like the tube where we've got air flowing through this carburetor. So this is the air flowing left to right as you're looking at it there. And you notice that in the center of this pipe, I have a constriction. And you notice that that constriction actually kind of looks like an airplane wing when I cut it in half. That's what that constriction is going to look like. So what happens is the air is moving through here. When the air hits this area in here, the cross-sectional area of that pipe gets a whole lot smaller. So the only way all those air particles can go through there is that they've got to speed up. So they're going faster through here than they are out at the beginning of that pipe. So what happens when that velocity goes up? Bernoulli's principle, remember that name? Bernoulli says if the velocity goes up, the pressure is going to go down. So I'm going to get a negative pressure. I'm going to get a vacuum. This is going to have a sucking action, is a negative pressure. So now what I do is I say, okay, I'm down here. I'm going to put a bowl full of fluid, of my fuel. So this is going to be my fuel down here. And I'm going to stick a straw in it. So that's literally what it is. It's like kind of putting a straw in a milkshake, although I wouldn't suck straw up out of fuel, that would not be good, but it's the same kind of thing that you do with a milkshake. With the negative pressure up here, it's going to suck some of this fuel, lift it up out of the bowl and up into this airstream up here. And if I do this right with small port sizes and everything, I can actually make that fuel atomize and come out of there in really small droplets. So then when I go out to the far end of the carburetor, when the area gets a little bit wider, I get past that restriction in there, the air slows down, but all those fuel particles are now suspended in the air. So they're mixed in the air, and that can go on down to the engine. So again, what I've got downstream here is I've got the intake piston down here. The piston is coming down, and it's drawing air through this carburetor. The air is coming in here. It's getting restricted. Low pressure. It's drawing up that negative pressure, that vacuum. It's drawing the fuel out of my fuel reservoir down here, and it's atomizing it and going into the engine. So that's the scientific principle. That's how it works. So the next thing we need to do then is dig a little bit deeper in, okay, what all is going on in a carburetor? That's a basic principle, but there's a lot of other things that are going in there to allow us to adjust the fuel flow rate, to control the speed of the engine, and so forth. So that's what we're going to tear into next.